Hey guys, Algebra 2. And this is week, today is the 30th, right? November 30th. So the first week of December, we're getting ready for finals in 2 weeks. So we got some notes today. We're going over quadratics. I went over these notes, sorry, in class today, but in case you weren't there or you want to watch it again, I'm making this video. So we're looking at notes 3.5a. We're going to do 3.5b in another video, and then I'll look at the homework. So consider this function. We're talking about quadratics, and today we're actually talking about the vertex form, which I might kind of go in a different order than I did in class, but consider this function here, f of x equals x squared. This is the parent quadratic function. This is the basic quadratic function. Every other type of quadratic function that you graph or solve is some child of this function, some transformation of this function. So complete the table of values for this function. So let's do this over here. I got my doc over here. So let's see. All right, so we got, again, f of x is equal to x squared. Right, there's that. And we got x here. We got f of x here. So we're making a little table here to kind of think about the values. They have it from -2 all the way to +2. And this function is just squaring values. So if you input -2, the output is just -2 squared, which is going to be +4. -1 squared is +1. 0 squared is 0, and then 1 squared is 1, and 2 squared is 4. And this is, again, is the basic idea here of a normal quadratic function. Because a negative value squared is positive, you don't have a line here, and we're doing multiplication. So when you graph it, it looks something like this. So here's the y-axis, here's the x-axis right here. So x, y. You have a point at the origin. So this graph has a point at the origin. And you have a point at 1, 1, 2, 4. And then I'll mimic that or reflect it over the y-axis. It looks something like this. 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Okay. Something like that. There's our quadratic. It makes a parabola. That is the shape it makes, that U shape, parabola. Call it what you want. There you go. And so let's think about this. Again, let me fill this out. I'll do my best to fill out the notes. If you want to print it out, you can write this out. If you didn't print it out, you can just take whatever notes you want. How you take notes is really up to you. Again, this is called the parent function. I'm going to make that a little bigger. Make that bigger. Let's see, format. There we go. The parent function. I do like blue though. Okay, that's the parent function. What is the vertex of this graph? So the vertex, again, is the highest or lowest part of the quadratic, of the parabola. So here, this is the vertex. That's the vertex. It's also called the minimum or maximum, depending on whether the graph opens up or down. This graph opens up, so there's a minimum. The vertex here is also the minimum. If this graph opened down, so you can have a quadratic that opens like this, right? Opens down, that has a vertex right here, where that would be the vertex of that parabola, and that has a maximum. This one has a minimum, and this vertex is at the origin, so the parent function is the origin, so it's at 0, 0. The axis of symmetry, every quadratic has a balance to it. It's symmetrical vertically. So there's a line that you can draw right down the middle that will cut through it. So again, if you want to think of the text, write this smaller. The axis of symmetry is a vertical line that goes down the middle of the parabola. And then right here, it's always x equals, and then I'm going to say it's going to be h, which you don't know what that is yet, but you'll know what that is later. Or if you already went to class, you know what that is. You should know what that is. So this is the axis of symmetry. Let me see if I can make that a little bit smaller. So it fits. But every quadratic has an axis of symmetry. But again, if I just draw a line like right down the middle, here's the y-axis. This one here, if you draw a line right down the middle, it would cut right through it, and it should be even on both sides. So, like for example, here, this point is 2 away from the axis of symmetry, and this point is also 2 away from the axis of symmetry. This point is 3 away from the axis of symmetry, and this point is also 3. Right? So 3 left, 3 to the right. 2 to the left, 2 to the right, and so on. So all the points here are the same distance. They're mirrored over the y-axis. So this has a minimum, and again, it occurs with the vertex here. So maybe I'll write this in. This one has a minimum that's at 0, 0. There it is. So here's the vertex. I'm going to skip E for now, and we'll look at this later. What about this equation makes the function quadratic? It's quadratic because it has a second degree term. Or second degree is the highest term. So I'd say second degree is the highest term. Meaning, again, there's some variable raised to the second power. That would be my second degree. Some variable raised to the second power. X squared. You have an x squared. Okay, that's really how you think about it. You have an x squared. If you have an x squared and it's the highest thing squared or highest exponent, then that's quadratic. So it's pretty easy to tell. It's actually really easy to tell. So I'm going to go ahead and, if you need to write this down, you can pause it. But I'm going to kind of clear all my drawings and then zoom in a little bit so we can start looking at some more. Zoom in here. Oh, I'll zoom in here. Okay. All right. So A here. I'm going to zoom in even more. A, is that a quadratic? Yeah, I mean, especially once you start to figure it out, it's super obvious, right? You have an x squared here. That's the highest x squared. So yes, that's quadratic. I'm actually going to make that blue. Blue is good. Blue is my favorite color, so blue is good. So is it a quadratic? Yes. There's an exponent, or there's a variable. Sorry, variable raised to the second power, something like that. That's the only thing raised to the second power. This is technically a quadratic trinomial, but yes, that is definitely a quadratic. Now let's look at the next one here. So this one here, there's an x squared, so that's there. So it does have an x squared, but there's also an x cubed there. And so the 2 isn't the highest degree. You have a third degree term. This is actually a cubic trinomial. So no, this is definitely not. This is not. No, it's not a quadratic function. It's actually cubic. Okay, so there's 2 down. Let's look at this. I'm going to now clear those drawings. We'll look at the next 2. Next 2 here. Okay, scoot over. There we go. There we go. Okay. Next one here. Is this quadratic? No, it's not. There's nothing squared. It's just 5x plus 7. This is linear. So no, this is definitely not linear. You know it if you graph it. If you graph this, it makes a line. The slope is 5. The y-intercept is 7. So no, not quadratic. Next example, you do have something squared here, but that's 3 squared, which evaluates to 9. So that's not a variable. That's just a constant being squared. So no, that is definitely also nope, not a quadratic. So no, that is not a quadratic there. I wish I should make this bigger. I want to make it even more obvious. It is not a quadratic. No, not a quadratic. Neither one of these quadratics, actually. Neither one of these quadratics. That's linear, and this is also linear. They're both linear. Okay, so let's keep going. And I'm going to skip this quadratic functions part for a second, and you'll see why. I'm going to go down to the next part of the notes. I'm going to zoom in a little bit more now. So again, the parent function, this parent f of x squared, has a vertex at the origin. The vertex is at the origin. It's at the origin, which is 0, 0. Put this text here. Where's that? It's at the origin, and I should make this a little bit smaller now. 24, I think it's fine. The origin is where this is, which again is 0. Right? And you can identify it from this form called vertex form. Now, not every quadratic has a vertex at the origin. In fact, most don't. But there is a form that we're going to learn about today, that you should have learned from Algebra 1, that makes it very easy to tell where the vertex is. And this is the vertex form here. And there's three things to know about. It's y equals a times x minus h squared plus k, where a stands for something, and h stands for something, and k stands for something. Let's zoom in just a tiny bit more. I want to make it a little bit bigger. There we go. There we go. Yep. Okay. Now I'll move this back right there. Or 0. Okay. So what is? I'm gonna start with h. H represents the horizontal shift. So h is the horizontal shift, right? Think h. Think horizontal. Right? They both have an h in it. Horizontal h. That kind of makes sense. That tells you how much is shifted left or right. Shift left or right. It's always the opposite way that you think it is. And that'll make more sense later. H is horizontal, so K, it's not easy, but it's not that easy to tell. K is the vertical shift. And I know there's no K in vertical. I'm putting that there to make it a little more obvious. K is the vertical shift, and it is actually the way you think it is. That one's not really different. But yes, K is the vertical shift. H is horizontal shift this way. K is the vertical shift up and down. A represents the direction of the opening, which is up, or down, and the I'll say whether the parabola is wide or narrow. Again, this will hopefully make more sense. Hopefully this is kind of reminding you what you learned in Algebra 1, but if you don't remember any of this, hopefully it'll make sense in a second. So a value decides whether it's wide or narrow, does it open up or open down. Those are the things that a decides. And the vertex of the quadratic function is always going to be at h comma k, if you're looking at this form. So if I see anything in this form, then the vertex is easy to find. I just look at h and comma k. Let's dive a little deeper into this, and I want to make it even make more sense. So Desmos. Desmos is a great way to look at this. So let's see here. Let's set a back to being 1. A is 1. And here we have, right now, you can kind of see, I'm going to move this for the time being. I'll put it back in a second. Don't worry about that. Make this a little bit bigger so I can see it more. Oh, I'm just going to clear my drawing. It's fine. Let's clear this. Hopefully you wrote that down because I cleared it all. So here we have our, in red, we have our normal parent function, but now I have it written in this vertex form. So x minus hk, where h here is 0, h is 0, k is 0, because the vertex of the parent form is at the origin. So look at what happened, and I encourage you to graph this. I encourage you to graph this as well. Notice what happens if I change h. If h is more positive, if h is a bigger value, that means that the graph shifts over in the positive direction, in the right direction. Now that might not be super intuitive, because if I was to write down what this graph would be, even though the h value is positive 6, this function, if I write as f of x equals, and I'll, here's that, I'll actually write what a is and everything. So a is 1. We don't usually write the 1 there. This is going to be x minus 6, even though you would think that that should be you would think if it's x minus 6, you might think it's shifted in the negative direction. Here it's actually shifted in the positive direction. So this is what it would look like if you saw it out. Actually, you probably wouldn't have the 1 there, and you probably wouldn't have the plus 0, but that's what it looks like. F of x equals x minus 6 squared, even though, again, the h value is 6 here. H is not negative 6. H is just positive 6, because the form here always has the minus there. If I made this x plus 6, it's actually, and I'll change the color so it doesn't get confusing. Make it green. Right, this green one here is actually over here on the left. It's in the negative area, even though it's x plus 6. It's actually in the negative side. It went 6 to the left. That's again because the minus there. This actually, the h value here is actually negative 6. It'd be minus negative 6, which is plus 6. Like notice here, if I make this h value negative 6, it moves in the negative direction, even though it'd look like plus 6. So h moves it left or right. And again, it's opposite of what you think. It's opposite of what you think. If it's x plus 6 here, you're actually moving to the left, negative 6. But for the most part, where h is kind of opposite of what you think, k is the exact what you think. If k is 1 or 3, it moves up 3. K just moves it up, right? So if k is 7 or 8, then it's just going to move 8, right? That's all it is there. This graph here would be, if I was to graph it, h is 5, so it's going to be x minus 5. And the k value is 8, so plus 8. So now that I hit this, bam, the green one's right there. The green one's right where it should be. So x minus 5 plus, ooh, not k, it should be plus. X minus 5 plus 8. That's what it should be with actual values. So that moves it up or down. Okay? So again, that should be somewhat intuitive. If you graph it yourself, it will start to make sense. I'm going to move everything back to where it was, the parent function. So again, both h and k are 0 in the parent function. Now let's look what a does. Again, I said a decides whether it's wide or narrow. So it's wide or narrow. So if a is going to be, if a is greater than 1, notice as a increases, this graph gets more narrow. It's more narrow. As a increases, it gets more narrow. If a is a 10, it's pretty narrow. If I make a 100, it's even more narrow. If I make a like 100,000, it almost looks like just one line because it's so narrow, right? If I make it, so if I get closer back, notice as it gets closer and closer to 1, it starts to get where it was. If it's between 1 and 0, like a decimal, like 0.2, it gets much wider. If I make it 0.1, it's wider. If I make it 0.09, even wider. 0.08, 0.07, 0.06, it's getting wider and wider and wider. Make it 0.2, it's pretty wide. Make it 0.02002, it's just going to get wider and wider and wider. It's not quite flat, but it looks flat because it's really close to 0. Now, if I make this actually 0, make it actual 0, it actually becomes a totally horizontal line. Now, if I make it negative, negative is the same thing as positive, but now just opening down. So if it's negative 1, that's the same thing as the parent function, but now just open down. That's all it is. If it's negative, if it gets more and more negative, it gets more and more narrow. Just like if it was 10, it'd be really narrow, but opening up. Now if it's negative 10, it's really narrow, opening down. Same thing with the decimals. If it's between 1 and 0, it's going to get wider. It's just negative, so it's going to be just opening down, right? 0.002 or 3, whatever. There it goes. So that's how you make it wide. So that's what the a value does. Once you kind of understand that, it makes graphing this really, really easy. It's not trying to be difficult. So now that we understand that, I'm going to look at these real quick, and it'll become super easy. It's super easy. It's almost too easy. That's how stuff works. If you learn it, it becomes really easy. So here, f of x equals x minus 2 squared. So you don't have the a value here. You don't see the a value. A value is 1, right? A value should be right here, right? That's where the a value goes. You don't see it because it's 1. There's also you don't see a k value, which means k is 0. So looking at this graph, Right now, A is equal to 1. K, the vertical shift, is equal to 0. And then H is actually equal to positive 2, just 2. Even though here it's minus 2, it should be positive 2. So if you're going to graph this, your vertex would be at 0. It'd be at 2, 0. So shift over 2, don't go up or down. Shift over 2, don't go up or down. And then it looks just like the parent function. You have a point there, go from the vertex over 1, up 1, from the vertex over 2, up 4. Same thing here. And there's your graph. Now I'm drawing with a straight line here, so it doesn't look great, but that's about what your problem looks like. Right? Something like that. Imagine it being a little more smooth, but there's your problem. So the vertex here, we see that it's going to be at positive 2, 0. The domain of almost all these functions, all real numbers. All real, 2 L's, no, 1 L. All real numbers. Because domain is your input, your x values, and it might not be obvious, but this graph is going to keep on expanding. Like at this point, when between -1 and 1, there's a distance of 2 between the points. Between these points, a distance of 4. And as you keep going, that distance is going to keep growing. And so it'll always be all real numbers. The range, well, the low point here is at 0. The lowest y value is 0, and then everything above it is above 0. So the range here is going to be, I would write this as y is greater than or equal to 0. And you can write like that. Domain, if you want to do all real numbers, you could write like this. Domain again, you can write that a couple different ways. You could write like this, infinity, sorry, that'd be negative infinity. Negative infinity to positive infinity. That's another way to say all real numbers. You could do the R symbol if you know that. A couple ways to write all real numbers. And you could also use the symbol for infinity, like the fallen over 8. The range here, you could say the range is between 0 and infinity, where you have a bracket over 0 because it can be 0, but it can't be infinity. So there's that. Next one, B. Same thing. You look at it. Immediately, you should be able to tell the vertex. It's plus 3x plus 3. So that means that the h value is -3. And it's plus 2, so the k value is positive 2. So there's your vertex at -3, 2, which means you would have a point, I'll do a different color, green, at -3, 2, right there. So there's the vertex, at -3, 2. I can go over 1, up 1, over 2, up 4, 1, 2, 3, 4 is about, about there. And then I can just mirror it. If I go over 1 this way, up 1, I'm going to go over 1 the other way and up 1. If I go from the vertex over 2, up 4 one way, I'm going to go up over 2, up 4 the other way. Right, and there it is. I'll do my best to draw some lines. Look something like this. It's not perfect, but I mean, it is what it is. Right? Looks kind of ugly, but whatever. You get it. It's opening up. There's a vertex at -3, 2. The range here, the lowest y value. Just think about where's the lowest y value. I'm going to do it in a pink so you can really see. Lowest y value would be right there at 2. It's greater than 2 or it's 2. 2 is the lowest point it is. So now, instead of y is greater than or equal to 0, y is greater than or equal to 2. That's how you can write the range. Or you can write the range like this. You can say bracket 2, infinity. And does it have a minimum or maximum? It has a minimum because that's the lowest point. That's definitely a minimum. All right, 2 problems down. Let's do a couple more. Clear that. Again, if you didn't get it, you can always rewind the video. That's a good thing about videos. The next two I'm going to do a little quicker. I'm not going to graph it here. I'm going to just use Desmos and talk about it. So I can get rid of this, maybe zoom this out a little bit. So see here, f of x equals -x squared. Just type it in. F of x equals -x squared. There it is. Where's the vertex? Well, this is just the parent function, but now opening down. So where's the vertex? The vertex is again at the origin, 0, 0. The range here. Well, now, before we were looking at the low point. Now we actually have a high point. Right? This is the high point. And the high point here is at y equals 0. Make it red, or orange, stand out more, right? There's the orange line. That's the high point. So the range, it could be anything less than 0. So I say y is less than or equal to 0. That's the range. And this, of course, has a maximum because that's the high point, has a maximum. One more we got here for this one. Move this up a little bit. Oh, why did it shrink like that? I didn't want to do that. Oh, let's move this over then. Okay, move this over. Right. There's D. Okay. So for this one, again, a value is -1. You see a negative in front right there. The negative, not actually see. There's the negative right there in front. So the a value is -1. The h value is -4. There is no k value. There's nothing there. Or the k value is 0. We don't see it, so 0. So before I even graph it, again, I should have some idea. It's going to open down. The vertex, that's going to be -4, 0. Right? The vertex here should be at -4, 0. Let's move 4 to the left direction. It's not moved up or down at all. It's just an open down. So pretty easy to graph this. Let's put it in Desmos. Oh, gotta get off that. Okay. Put in Desmos, so negative, plus parenthesis, square that, and then inside parentheses be x plus 4. And there you go. All right. That's the vertex again. -4, 0. It opens down. The domain against all real numbers, and the min-max. This has a minimum. Sorry, it has a maximum. Sorry, it has a maximum. The maximum is at 0 at this point, -4, 0. The maximum y value is 0. Okay, so hopefully that's, again, ringing some bells, some of Algebra 1 coming back to you. So A through D, just graph these, and you should be able to get them. The axis of symmetry is the line that cuts right down the middle. So I'll look at one. Let me zoom in and look at one really quick. So here you have this graph, f of x equals x minus 1 squared minus 5. So immediately you can tell the vertex. The vertex, if it's x minus 1, opposite of that, so the positive 1, minus 5, so it is minus 5. There's your vertex. And then if you're to find the axis of symmetry is always going to be, so axis of symmetry is always x equals h. X equals h here. That's what it always is. And if you know that, it makes it pretty easy. But if you want to graph it, just double check, you can do that too. So let's graph this really quick. Let me go and X out some of this stuff. So it's f of x equals x minus 1 minus 5, right? There's our graph again. We said there'd be a vertex at 1, -5. There's that vertex at 1, -5. The axis of symmetry is just x equals h, which here is 1. Here you see, I'll change it to green. Green, I'll make it dash. See how this dash line cuts right through the middle of that one. So that's what the axis of symmetry is. So it's always h, whatever the h value is. So without even graphing B, I can look at it. And I know that the vertex, I don't have to graph it at all. I know the vertex is going to be, again, it's x plus 3, so that's going to be minus 3, plus 4, so plus 4. So there's your vertex, -3, 4. And then, again, axis of symmetry is just x equals h. So here, the axis of symmetry would be, writing it down here, x equals -3. And again, if I graphed it, I could prove that this is right. So it's negative here, so it opens down. X plus 3 plus 4. And then the line should be x equals negative 3. And there it goes. See, right there. Right down the middle. Pretty easy. And that's pretty much up to the notes. You could look at the last question. We'll talk about this a little bit in the next video, but how it goes. You can tell the vertex right away. If you look at this, it should not be hard to tell the vertex. Over 1 up 2. The vertex is 1, 2. Meaning that, again, h is equal to 1, k is equal to 2. So now you're asking, like, how do you find the a value? So we talked about a little bit for a second. Let me go back to my document. This idea that in the parent function, if a is 1, because a is 1, the parent function, normally it's going to be over 1 up 1, over 2 up 4, over 3 up 9, because 1 squared is 1, 2 squared is 4, 3 squared is 9. And then you can find out really how to graph it easier if you know the a value and how to multiply it. So if a equals 1, then nothing changes. And where if you go over 1 from the vertex, you go up 1, right? If I show some examples here, so let's see. So I'm going to make this one really quick. I'm going to change it to be positive 1. Notice you have a point here. Again, your vertex here is going to be at negative 3, 4. There's that point. There's also a point here at negative 2, 5. Right? This blue dot, because it went over 1, up 1. If you go from the vertex again, if you go over 2, up 4, 1, 2, 3, 4, that should be at negative 1, 8. Right, there's this point here. It's easy to find it because I'm going over 1, up 1, over 2, up 4, over 3, up 8, up 8. So I know like the vertex over 3 will be at 0, up 8 should be at 12, right? And there's, sorry, not 12, 13, right? And this perfect one's on there. So again, I'm just going over 1, up 1, over 2, up 4, because 2 squared is 4, over 3, up 9, because 3 squared is 9. So once you know that, if you look at this problem here, it's clearly going over 1, up 1. It's going over 1, up 1. So if you want to know, what that equation would be, a value is 1, so f of x equals a value is 1, so I'm not going to put there, and it's going to be x minus the h value, which is 1, x minus 1. That value squared, and then plus 2. So hopefully, again, this is what we went over in class. If you missed class, hopefully these notes help. We're just looking at quadratics in vertex form. A little over 30 minutes. I'm done talking. So I'll see you guys later with hopefully another video on the other part of the notes.